Okay, so our today's agenda is as follows. Practice example 2 for device sizing. Second is simulating equal sized CMOS and unequal sized CMOS inverters. And third is studying non-ideal IV effects, also known as short channel effects. Under that, we have to study velocity saturation, mobility degradation, body effect, channel length modulation, tunneling, and temperature dependence. So, if you remember, in the last session on 6th of November, we had solved one numerical um, which implemented our conclusion that in order to have equal rise and fall time in a CMOS inverter circuit, we must have the width of PMOS 2.5 times the width of NMOS. And we also made a point that the length of both PMOS and NMOS is equal to the target technology given in the numerical, which can be 90 nanometer, 100 nanometer, 120 nanometer, 180 nanometers, anything. So whatever is the technology given in the numerical, our LP is equal to Ln equal to L. And the next fact is that the width of NMOS should be 1.5 times the length of NMOS, and the width of PMOS should be 2.5 times. So we also had justified that for silicon, the electron mobility is 650 centimeter per volt second. The mobility of holes is 270 centimeter per volt second, and the carrier mobility ratio comes out to be 2.41. And then we had taken a numerical which asked us to design a CMOS inverter to have T rise equal to T fall for 120 nanometer process. So we had solved the numerical in this way, is that we first drew the circuit for CMOS inverter and we did not write the widths and lengths, but we represented the W by L ratio as WP by LP for PMOS and WN by LN for NMOS. And we have termed WP by LP as a small p, that is size of PMOS, and Wn upon Ln as a small n, that is size of NMOS. So we have written certain equations here. Because it is 120 nanometer process, L is equal to 120 nanometer, LP equal to Ln equal to L equal to 120 nanometers. So out of the 4 unknowns in this numerical, 2 unknowns are automatically given in the numerical. And we said for reliable operation of NMOS, the size of NMOS should be 1.5, and because size of any NMOS is W upon L, so we get Wn by Ln equal to 1.5, Ln is 120, so Wn comes out to be 180 nanometers. So the third unknown is also found, and we told that for rise time equal to fall time, Wp is equal to 2.5 times Wn. Wn was calculated as 180, so Wp came out to be 450 nanometers. And then the solution of the numerical was given by writing the widths and lengths of the MOSFETs. So we had noted here that the size of NMOS is 1.5, the size of PMOS is 3.75, and the relative size is 2.5. So always remember one thing, there are 3 numbers which are important in device sizing: 1.5, 2.5 and 3.75. So understand 1.5 is size of NMOS, 2.5 is the relative size of PMOS and NMOS, and 3.75 is the size of PMOS. So always understand the significance of these 3 numbers. Okay, so we have written here that 3.75 is size of PMOS, 1.5 is size of NMOS, and relative size is 2.5. So same results we are going to also use for solving one more practice numerical. Okay. Design a CMOS inverter for 180 nanometer process such that trise equal to tfall. So we can say given process is 180 nanometers equal to L. Therefore, length of PMOS is equal to length of NMOS is equal to L equal to 180 nanometers. This is result number 1. Okay. So we can say this is the first one. Second is N, which is the size of NMOS, is Wn by Ln equal to 1.5. Therefore, width of NMOS is 1.5 times Ln, which comes out to be 1.5 into 180 nanometers equal to 270 nanometers. Third, width of PMOS is 2.5 times width of NMOS, which comes out to be 2.5 into 270 nanometers is equal to 675. So we have found 1, 2. We have found Wn as 270 nanometers, Wp as 650 nanometers. Okay. So now as a solution we can draw the CMOS inverter, write the dimensions. So 675 by 180 nanometers is the size of PMOS and 270 by 180 is the size of NMOS. So we can also verify our important numbers. So we see here that this ratio is equal to 1.5, that is the size of NMOS. This ratio is equal to 3.75 size of PMOS, and we see here that the relative size between PMOS and NMOS is 2.5. So always be clear about size of PMOS is 3.75, size of NMOS is 1.5, and relative size is 2.5. So which is equal to P over N. Okay. Now what we do is that we actually do simulations of equal and unequal sized CMOS inverters, and here we are going to take the previous numerical into account. Okay, so simulating equal sized and unequal sized CMOS inverter. Okay, so here for equal size. So we are going to take 120 nanometers as our process. Okay, we will see if we are having 120 nanometers foundry available. So for equal sized we have WP 600 nanometers, LP will be 120 nanometers, WN will be 600 nanometers, and LN will be 120 nanometers. And for unequal sized, we have 1.5 times ln, and WP will be 450 nanometers. Okay. So what I will try if I can get 120 here, and so it has not allowed me to make the channel length as 120 nanometers. Let me see if I am having a ready-made 120 nanometers foundry. So I'll go to file, select foundry, and I will just see what is this CMOS 012 dot rule. So when I do this, I get 5 lambda as 300 nano, lambda as 60 nano, and technology is 120 nano. Correct. So we have actually selected 120 nanometers foundry. So here, when I do like this, I can clearly see here that length is coming as 120 nano, and I will make it 0.6. So it is size equal to 5. Okay. So yes, it is there. So then I take NMOS, and yes, it is still. So I am now making an inverter with equal size PMOS and NMOS. So I go here. So this is my inverter with equal sizes. So it is 600 and 120. So now I will use sizing 450 120 is for okay. PMOS 450 by 120 and MOS is 180 by 120. So we applied same frequency clocks to both of them. Let us see. So what we will do is that we will first switch off the visibility. Okay, anyways, it can remain like that, no problem. So I will switch off the visibility of V into because both of them are having same frequency. So I will say V into and say not in simulation assign. I will keep this as visible. Output is also visible. We see that both the inverters are giving a complement of the output. So V out is a complement of V in one. But now we have to see about the rise times and fall times. Yes, so we see here, please see carefully. The third waveform which is in red color, that is it is written V out unequal sized. We see here after few cycles, I am having rise time equal to fall time 4 picoseconds and 4 picoseconds. 4 picoseconds and 3 picoseconds. So it is there. Let us see if we are considering more number of cycles. You see here after some time it is becoming 3 picoseconds, 3 picoseconds. So when I am using um, properly sized PMOS and NMOS device in CMOS inverter, then I am getting equal rise time and fall time. Let me see when I'm using equal sized, am I getting T rise not equal to T fall? Let us see. So unequal sized, maybe I'll say equal sized. See here. Okay, for equal sized inverter, rise time is 4 picoseconds and fall time is 2 picoseconds. We see here afterwards it is becoming T rise equal to 4 pico, T fall equal to 2 pico. And if I see make it unequal sized and if I say reset, then I'm clearly seeing that my rise time is becoming equal to fall time 3 pico and 3 pico. This is how you can do it. I'll save this now. save as. Okay. So you can write down here 4 picoseconds, 2 picoseconds, 3 picoseconds, 3 picoseconds. Okay. Thus, using properly sized PMOS and NMOS devices, we can achieve T-rise to T-fall. Okay. Now we go to the third topic, non-ideal IV effects. Okay. So if you remember, we had actually defined short channel, long channel MOSFETs. We told before that if the channel length L is much greater than the junction depth of the MOSFET, then it is called as long channel MOSFET. And if channel length L is much lesser than the junction depth Xj, it is called as short channel MOSFET. Okay. Velocity saturation. So the name itself conveys to some extent what we are going to discuss. Okay, velocity saturation. Okay, so some of the formulas which we are going to write here will be definitely known to you, but just we are going to apply them to a MOSFET structure. Okay, so we know that the carrier velocity denoted like this is given as V equal to mu into E, where mu is the carrier mobility and it is given in centimeter square per volt second, and E is the electric field in volt per centimeter. Okay, so if we apply this formula to the MOSFET structure, we told before that the velocity V in the lateral direction. So when we say lateral, so lateral actually means like this. So in our case, it actually means from source to drain or drain to source. So if it is an NMOS, then carriers will flow from source to drain and the electric current flows from drain to source. If it is a PMOS, then the holes will flow from drain to source and the electric current will whole current will flow from source to drain. So you know that the direction of flow of conventional current is opposite to the direction of flow of charge carriers. When we say that lateral velocity v lat, we can say it is equal to, okay, so rather writing we will write v lat will be given as mu n into the lateral electric field. Okay, so we can write down that mu n now becomes the electron mobility and E lat is the lateral electric field and we already defined this before that it is equal to drain to source voltage upon the channel length L. Okay, so as such we can conclude that therefore V lat is proportional to the lateral electric field. Okay, fine, but this is applicable only for low electric field or weak electric fields, only for weak electric fields. Okay, so but the lateral carrier velocity saturates to a constant value V sat for high electric field. Now why does high electric field come into picture here? Because the lateral electric field E lat is equal to drain to source voltage upon L, but due to technology scaling, L goes on reducing, thereby increasing the value of E lat. Okay, that is why we say that velocity saturation is a effect which is a short channel effect, because short channel means smaller values of L, and because L reduces, because technology scaling has to be achieved. That is why automatically the lateral electric field goes on increasing, and then the lateral velocity of electron no longer remains proportional to E lat. Okay, so we can say that V sat is called as saturation carrier velocity, which is equal to the lateral velocity for E lat equal to E sat. Okay, hence we can plot a graph of V lat versus E lat. Saturation field strength So there are some facts which have been given by semiconductor manufacturers, which are as follows. For 2 micrometer channel length, MOSFET shows velocity saturation at VDD equal to 4 volts, while for 0.18 micrometer channel length MOSFET shows velocity saturation above VDD equal to 0.36 volts. Okay. Yeah. So V lat is equal to mu into the lateral electric field upon 1 plus E lat on E sat. I can say question number 1, question number 2, 3, 4, 5. Okay. Now you come to the second effect, that is mobility degradation. So if you remember clearly that velocity saturation, okay, yeah. So maybe we can make a point here now. Is a conclusion of velocity saturation. We can say thus velocity saturation is a short channel effect caused due to VDS and reducing channel lengths. So velocity saturation is a short channel effect caused due to VDS and reducing channel lengths. So just like velocity saturation is a short channel effect caused due to VDS and a reducing channel length, mobility degradation is an effect which is caused due to VGS and the oxide thickness TOX. So that is strong lateral electric field ELAT. Remember this thing now. Unlike velocity saturation, which is caused by strong lateral electric field ELAT, strong vertical electric field EVER causes the charge carriers to scatter against the surface and thus reduce the carrier mobility mu, which is known as mobility degradation. Okay, so there is mathematical modeling available for this, but then it is out of the scope. That is why we can just understand that while velocity saturation is an effect, is a short channel effect which is caused by strong lateral electric fields ELAT, strong vertical electric fields EVER causes the charge carriers to scatter against the surface and thus reduce the carrier mobility. If you remember, we had defined EVER as follows. Is equal to VGS upon Tox. Okay. Have you come to body effect? So body effect is something I think you have already studied in your second year, but I do not know how much you remember. Okay. So So body effect is usually seen when we connect MOSFETs in series. Okay, so if you remember, consider the transistor level schematic of a 2-input CMOS NAND gate as follows. P1 parallel P2, N1 series N2. Okay, so what we will do is we will only consider this section, that is pull down network, and we'll zoom it now. We are going to consider the body terminal also here. So if I show the body terminal, then it looks like this. Similarly, the second NMOS. Okay. So we have B2, B1. Drain of upper, source of upper, drain of lower, source of lower. Okay, and we have gate of upper, we have gate of lower. Okay, so we can show that the threshold voltage of the upper transistor, so this is N2, this is N1, VT2, VT1, and most important is this potential VSB2, and here we have VSB1. So it is very clear from the circuit diagram that the source of the NMOS N1 is reference to ground VSS. So we will be having VSB1 equal to 0, but VSB2 will not be equal to 0. This is called as body effect. Okay. So we see here, whenever the source to body voltage is equal to 0, then it is said to be no body effect, and whenever the source to body voltage is not equal to 0, it is said that the body effect is present. We have already told before. Okay, so we can conclude about figure number 2. We can say figure 1 and figure 2. We can say first that when the potential difference between body and source terminals is 0, that is when VSB equal to 0, we say that body effect is absent. Hence VSB not equal to 0 indicates presence of body effect. Okay, now we come to mathematical modeling of body effect. So Vt equal to Vt0 plus gamma into under root of phi f plus Vsb minus under root of phi f. So what are these terms? Vt is the threshold voltage. Vt0 is the threshold voltage in absence of body effect. Gamma is called as body effect coefficient, which is given as oxide thickness upon the permeability of SiO2, silicon oxide, into under root of 2 into charge of an electron into the permittivity of silicon material into the acceptor impurity doping concentration. And because epsilon ox upon T ox is C ox, we can rewrite the same equation as 2 into Q into epsilon Si into Na Na upon C ox. Since C ox is equal to epsilon ox upon C ox. VSB is 5F is known as a surface potential, which is given as 2 times the voltage equivalent of temperature into natural logarithm of acceptor impurity concentration upon intrinsic concentration. And some constants in all this mathematical modeling is note that epsilon ox is epsilon 0 into epsilon r for SiO2. It is equal to epsilon 0 into 3.9. First, epsilon silicon is absolute permittivity into relative permittivity of silicon, which comes out to be epsilon 0 into 11.7. Similarly, third constant is intrinsic doping concentration for an NMOS device is given as 1.45 into 10 raised to 10 atoms per cc. Okay. Fourth, voltage equivalent of temperature is equal to Boltzmann constant into the temperature in Kelvin upon charge of an electron, which comes out to be approximately 26 millivolts for temperature equal to 27 degrees centigrade equal to 300 degrees Kelvin. Okay. And fine. In absence of body effect, that is VSB equal to 0, equation number 1 becomes Vt equal to Vt0 plus fitting parameter surface potential plus 0 minus surface potential, which becomes nothing but equal to Vt0. Okay, therefore we say Vt0 is equal to Vt for Vs equal to 0. Okay. Okay, so consider the equation of IDS in NMOS device for pinch off region IDS is equal to K dash upon 2 into VGS minus VT whole square. Okay, where K dash is equal to mu n into epsilon ox upon T ox into double while ratio. Okay, so we see here that IDS is equal to K dash upon 2 into VGS minus VT whole square. It is not a function of drain to source voltage. Okay, and since VGS and VT are constant, while plotting the family of curves. So this is data sheet. It's a data sheet parameter. Why we said family of curves? Because it is always plotted as IDS versus VDS for VGS equal to K1, K2, K3, so on. That is why I said that VGS is constant while plotting family of curves. So that is why we can say that IDS is equal to IDS SAT, which is not a function of VDS. Okay, but please understand that the above holds true only for long channel devices. Okay, This is most important, which explains about channel length modulation. For short channel devices, IDS is given as IDS is K dash upon 2 into VGS minus VT whole square into one more factor 1 plus lambda into VDS. Okay, so this is equation number 1, which applies only for long channel devices, and this is equation number 2. So you see the difference between equation number 1 and 2 is the only factor 1 plus lambda VDS, where lambda is called as channel length modulation parameter. Okay, and lambda L equal to 2 micrometers, L equal to 1 micrometers, NMOS, PMOS. Okay, so the value of CLM parameter for NMOS device L equal to 2 micrometers is 0.01. When it increases to 0.04 when the device becomes smaller. In case of a PMOS device, it is 0.01 for larger devices and 0.05 for smaller devices. Okay, so we see here clearly that when the target technology goes on improving, when the device becomes smaller, we see here clearly that the channel length modulation parameter has increased from 0.01 to 0.04 and from 0.01 to 0.05. What is the effect basically? So initially we see in equation number 1, IDS was not a function of VDS, now it has become a function of VDS. Okay, so I can actually write down like this, that is now a function of VDS. This is a change. So what is the effect? The effect is this. This is family of curves, and this black colored lines indicate equation number 1. Okay, and because of the addition, so if we see that equation number 1, IDS is not a function of VDS, so as VDS increases, still IDS remains constant, but because of channel modulation effect, what we get is this. Now the drain current no longer remains constant. Okay, so we can say that okay.